Hello, today we're going to be going over the problem ST path using DFS. Um, this is a pretty straightforward educator problem, but let's get right into it. So given a directed graph and two vertices where one is the source and the other is the destination, in that case S is for source and I guess T is for destination, we want to find if you can get to T from S using the graph's paths. And we're specified to use depth first search technique here. So let's just go ahead and do that. One little bit, obviously when we do depth first, we're going to find it eventually, given enough time to run over everything, but this isn't necessarily going to find the shortest path. If you wanted the shortest path over an unweighted graph, you'd want to use BFS. Okay, so our graph is an adjacency list. The function has the following signature with DFS. It's going to take in the graph, it's going to take in the source, it's going to take in the destination. And so we have this graph class defined. Notably, it gives us the number of vertices, which is super helpful. And then the things are represented as an adjacency list. So it's a vector of integers, right? And then we have our constructor. So let's just kind of run through this example input. Let's just do it by hand and see what shakes out. So I'm going to move this over here. And so now we can see a graph. So right here, I've defined a stack for us. And then over here, I've defined a visited set, right? Because what do we need to know? We need to know, okay, what's the next thing we're going to visit, which we put on the stack. And then we have visited, we keep track of what we've already seen so we don't end up in an infinite loop. So S, let's say, is our source, right? Because we're using this test case where it's 8, 0, 7. So that means there's 1, 2, 3, 4, 5, 6, 7, 8 nodes. And then we're given the edges, and then we want to go from 0 to 7. So let us do that. So I'm going to come back over here. So let's start with 0. So initially, we're going to say, okay, we are going to put 0 in our visited. We're starting there. We've seen it. And we're going to put it on our stack. Now the main loop begins, right? So we're going to say, okay, let's pop 0 off the stack. This is what we're looking at now. And let's go through all of the neighbors of 0. So what are those going to be? Let's look at 1 and 2. Now 1, we can put that on the stack. 1 is not our destination. So if we find our destination, we're just going to turn right away. But right now, 1's not our destination. So we'll just say, okay, put it on the stack. Next, we look over here and we see, oh, look at that. That's 2. So we'll put 2 on the stack. Neither of them are our destination. So now that they've gone on the stack, where they're pushed on, each time we put on the stack, we'll also say we visited it so that if there's ever a path to one of these things that we've already seen, we don't keep going back and forth in circles forever. Okay, great. So it looks like the way we've picked these arbitrarily, now the thing we want to look at is 2, right? So what are we going to do? We're going to pop 2 off the stack like we said, and now we're looking at 2. So what can we get 2 from 2? Well, there's 6 right here, right? And so we'll put that in visited, and we'll pop it right here, or not pop. We will push it to our stack right here, and 6 is not our destination, so we keep looking. Okay, so we visited 6. We're going to pop this off, and we're going to start looking at 6 now. 6, you can't go anywhere from here. So our DFS is going to backtrack now. So just as a kind of a recap of the direction our DFS is going, we've gone here, then we went to here, and there's no more paths left, and there's no more paths left from 2 either. So now we're going to start looking from 1. So now we can just, I guess, I'll erase this. So now the path we're looking at starts from 1. So what are the neighbors of 1? Well, we can do the same routine. We'll pop 1 off the stack, and we'll start looking at it. Okay, so 1 only points to 3. So we'll just put 3 in visited because we're visiting it now. We'll put that on the stack. And we repeat the process. So let's see. 3 points to 4 and 5. So we'll just put 4 and 5. Or sorry, take 3 off the stack. Now we're looking at 3. We put 4 and 5 on here. And then we will mark those in visited. And then we will continue the process. So I'm just going to skip a couple steps. 5 is a dead end. So we look here. There's nowhere else to go. We go back. Now, no, I forgot to pop off 3. That would have been done already. Now we look at 4. What's that? 4 points to 7. But 7 is our destination. And since we only care if there is a path, not what that path is, at this point we can say, oh, okay, 7 is within the path that we're doing on our DFS. Therefore, there is a path from S to T 0 to 7, and we can return true. And so that's just going to be the general algorithm that we use for completing this problem. So it should be pretty quick from here on out. All right, so here I have my editor pulled up, and we can just get right into implementing this. So first of all, what are the data structures we're going to need? Well, we need to have our stack to keep track of what we are looking at next, and we need our visited set. So let's just do that directly. I already have the includes up here. and this so we have a code completion. But let's do it. So let's say we are going to make our visited set first. It is going to be a set of, looks like, yeah, we can just make it integers because each node is indexed with a number. So we can say set of int. We'll call it visited, and we'll just have it be empty for now. Next, we need a stack for the things to look at. So let's just call it S, right? So we'll say stack, and again, it's integers because that's the nodes, and we'll call it S. Okay, so we have our two basic data structures. Now what are we gonna do? Well, if you recall, what we did first was we said, okay, let's put our source onto the stack and put it in visited right away, and then we can start our main loop. So let's just do that. So let us insert, source into our visited set, and let us also put it onto the stack. So we'll push, that's the method in C++, we'll push that on the stack. Great, so now we can do our loop. So I'm just gonna let this autocomplete. So what's our condition? Well, if we run through the whole stack after pushing everything on, and we go exhaust all the possible nodes in our DFS, and we still don't find our node, then the stack will end up empty, and then we will have failed, basically. There is no SD path. So we'll say while our stack is not empty, and that is a method, we will do the actual DFS. And then at the bottom here, we can just say return false. If we make it through all of this, we don't find anything we're looking for, then we know we have failed to find an SD path. Okay, so now let's just go through the algorithm we spoke about. So we're here. First, we're going to pop the thing off the top of the stack, save that as the vertex we're looking at, and then we can start putting all of its neighbors on the stack. So let's say the one we're popping off the top, or the one at the top of the stack, is u, right? So let's say int u is equal to s.top. Great. So that's going to give us the value of the thing at the top. And then just another thing in C++, if you remember, top and pop are separate operations. Top will just return the object there, but it won't remove it. Pop will remove it, but it won't return anything. So we just need 2 lines of code there. So now, okay, we have our vertex to look at. So now we need to think, okay, how are we going to go through all of the neighbors, right? Because it's easy on a graph. You just look, okay, well, there's a line going this way, there's a line going this way. But what do you do about that in our implementation? So we can just check what our graph structure looks like, our graph class. And it looks like we have a vector of integers, right? So for each vertex, it's going to have a number of edges, right? So the adjacency list at edge source, so the vertex we're looking at, all of its destinations are going to be in this list. So we can just access how that's indexed from here. So let's go through all of the destinations from our source vertex that we're looking at, which in this case is u. So let's do a little for loop. So let's, it's going to be an integer, right? So yeah, for every integer in the graph's adjacency list, for every integer in the graph's adjacency list, which remember, I need to specify for, I'll call it v for vertex, right? So for every vertex in the graph's adjacency list for u, the source that we're looking at, we need to, do our algorithm, right? So that's going to be visit it, put it on the stack. But first, obviously, if it's our destination, we want to just say, okay, we're done. We found what we wanted. We know there's a path. We can return true. So if v is equal to our destination node, then we can just return true. We're done. No need to process anything else. We have found what we wanted. Of course, else, what we need to do is visit it and then put it on the stack. So let us do that now. So first of all, we need to make sure that we haven't visited that node already, right? Because otherwise we're going to be going in an infinite loop. So first we need to check if the node we're looking for isn't visited. And the idiom for that in C++ sets is we're going to check, okay, if visited, oops, sorry, not visit, if visited.find, right? If we look for v in our visited set, but it returns the iterator to the end of that set, then we know it's not there. So we only want to do it if it's unvisited. So this is basically saying, sorry, that's a VHDL comment, if unvisited, proceed, right? And that should be 2 E's. Proceed. Okay, so if it is, if it is unvisited, what are we going to do? Well, we are going to insert that into our visited set like we have up here. So we'll say visited.insert v. V is the vertex we're looking at. And then finally, we will push it onto our stack. So we will do s.push v. And so that'll do it. That's really all we need. So this will help us run through all of the test cases here, and it will eventually either find the destination and return that here, or if it gets through everything, it exhausts the stack and there's nothing left, then we will return false. So let's run our code real quick, make sure it works. I'm always capable of making mistakes in these. Let's copy this. This is our function. Let us paste that in. We'll run our code first, make sure there's no glaring errors. Yes, we didn't declare set. So I will take all of the headers we used. Actually, as a pro tip, if you include, sorry, I spelled that wrong, bits standard C++.h, that is just going to be all of the standard library headers, right? So you don't need to manually specify. Obviously, in a project or something, it's important that you pick and choose, because this is otherwise like maybe not the greatest practice, but for the purposes of these problems, this is fine. You can just do this and you don't have to worry about including stuff. So let's submit our code. And would you look at that? We have passed all the test cases. So that is how you find the ST path using DFS in this educator problem. I hope this was helpful. Have a great day.